Everyone, welcome back. In this video, we are going to understand Spark DAG. And again, this is something really fundamental and really important to be able to understand how Spark works under the hood, right? I've also made a video on how to read Spark query plans. And if you've not already watched it, please go ahead and watch it because that sets an overall base and context for this video as well. It is going to make a lot of things easier for you to understand. So now let's get started with the code. So here I'm basically trying to import a few modules and finally setting the Spark session. And before we go deep into the code, here is the list of topics that we are going to discuss in details. First one is reading files. We are going to look at how the DAG looks when you read files. Then we are going to cover narrow operations. So narrow operations are basically those operations in which no shuffle is involved. And we are going to simply look at filtering, adding or modifying columns, and then finally selecting relevant columns, right? And then we are going to look at wide operations. Two types of wide operation. The first one is a join, and we are going to cover two types of join, which is a sort merge and a broadcast join. And then we are going to go to aggregations using groupBy, right? So we are going to cover two methods, which is sum and count, which behave more or less similarly when you look at from the DAG perspective, how the DAG is generated, right? And then a count distinct, which behaves a little differently. The DAG is a little different. So now let's get started. We are going to read in a file, and this is a transaction file. Now all of this data set and the code will be present in my GitHub, and I'll be putting a link to my GitHub in the description, so don't worry about where this data set is coming from. So I basically read in a file and I print the number of partitions, and the way to do that is simply do a .rdd.get num partition. So I see that there are 13 partitions, right? Now I do a dot show. I call an action which is dot. Let's see how the job, how the UI looks like. So you see that there is a job that is created for showing a string, and that is good because we generally know that a job is created whenever an action is triggered, and show is an action, right? But what is not quite interesting is you also see a job for a Parquet file, right? And reading a Parquet file, reading this Parquet file is not an action. So why does Spark create a job? So the reason why Spark creates a job is because it simply reads in metadata, right? So metadata can be things like the number of partitions, the number of columns, the size of your data set, the type of column. So all of these things can be your metadata which Spark reads in to be able to optimize the execution downstream. So that is why you see two jobs being created, and because there is no shuffle, each of these jobs would simply have one stage, right? So you just see one stage. If I just go to the stages, you see one stage. Now a very important thing to note here is the show string has an input because it reads in a file, but the first Parquet doesn't have an input because it just reads metadata, right? Now that is how your jobs and status are going to look like. Now let's have a look at the DAG. So in the DAG, you see that is scanning a Parquet file, and the Parquet file has total 163 parts, which is 163 files, and then finally it does a columnar to row. So for those who have already seen my previous video, they would know that Park Parquet dataset. Parquet dataset is a columnar dataset, right? It stores data in the form of columns, right? So Spark basically anticipates that whenever it needs to do downstream transformations, the row format is going to be better, right? For those transformations, and that is why it converts columnar to row. And finally, you see a collect limit of 6 because we've done a show of 5 over here, and the sixth one basically for this header. So that is why you see a collect limit of 6. And This is something very important. Why does it show 163 files? Because if we if I simply go to my dataset and the transaction dataset, you see that it starts from the 08 part 0, and then it goes all the way to part 162. That means it has 163 parts in total, and that is why it reads in these 163 files. Now if we were to run a customer file, we would see something very similar. So let's go ahead and have a look at the job. You see something very similar. It reads in the parquet file, and then it again does a show string, and the DAG would also look similar, right? It basically read in one file because there was only one file for customers. If I go to the customer dataset, there is only one part, and that is why it just read in one part, and then it does the normal drill of columnar to row, and then finally a collect limit of 6. So now a very interesting point to note here is that what is this batches, right? Number of input batches, and then it prints, it basically takes in 4096 rows. And if I were to look at the transaction DAG also, I would see something similar. It also read in one batch, and it basically took 4096 rows, 4096 rows from here. Yeah. Now, batches basically is a group of rows, right? And Spark very smartly figures out that when you're reading data, for example, from a cluster, what it does is that on several executors, it is going to have partitions of data, right? And Spark figures out that hey, this guy is only asking me for 5 rows. Now, for getting 5 rows, I don't need to read all of the partition, right? I'm just going to take one of the group, right? One of the batches over here. Again, batches are not same as partition, but it is simply a group of rows. It takes in those groups of rows and it gives you what you need. It gives you those 5 rows that you need, right? So this is how basically your DAG is going to look like when you're going to do a read and a show. Now let's move on to narrow transformation. So for narrow transformation, we are doing a filter, and then so simply filtering by Boston, city equals Boston, and we add in 2 new columns, the first name and the last name, right? And the way we do that is simply by splitting the name on the space and then selecting respectively the first one and the second one, right? We modify the age column by adding the number 5 to it, and finally we select the relevant column, right? Now an interesting thing that you may note here is df, I'm trying to write this data frame, right? And writing is an action. So basically this is going to trigger a job. I could have also done a dot show, but as you've already seen, a dot show simply reads one batch, right? But what if I want to read the whole data set, right? If I want to read in the whole data set, for that I simply just did a write operation. So for writing the whole data set, it has to also read in the whole data set, and this is just for testing purposes, right? Another very important point to note is that the format noop over here. So this format also means NOOP, which stands for no op, which also means no operation, right? So it is going to simulate a write, but it is not actually going to write. And this is very useful for testing purposes. So here we are going to write, simulate a write to be precise, and then you see the job. You have one job for the save, and because there is no shuffle, there should be just one stage. And here you see there is just one stage wherein it reads the input data. And let's have a look at how the DAG looks like. So in the DAG, it basically read the number of files, read one files, and it read 5000 rows from that file. And if we were to just look at how many rows are there, it just had 5000 rows. That means it read in the whole data set. It does the normal drill of columnar to row, and it does a filter. It does a filter on city equals Boston, right? The logic that we added over here. And you would wonder, where is all of this gone? You don't see a step for that. And all of that has been put inside the project. So if you look at the black box inside of project, you would see that all of those transformations, the splitting, adding of 5 to age, and all of that has been added over here. So it's equivalent to doing something like select of something. So inside a select, when you write a SQL query, you're allowed to put in a column. You're also allowed to put in certain operations. So for example, let's say you want to do a cast of a column, right? You want to cast it from string to integer. You can also put it in the select. So you can assume something similar is happening over here, right? So all of those operations go inside the project, and finally it simulates a write. Yeah. So that is what happens over here, and basically this is how your DAG is going to look like for a narrow transformation. Now let's move over to wide transformation, and the first one is a join. Now, because my second data frame is very small, it's in kilobytes, Spark is naturally going to try to broadcast it. And in order to disable that default behavior, I'm going to set the Spark SQL auto broadcast join threshold to -1. And let me go ahead and do a join and then trigger a job. Now, before we trigger a job, let's just see our Spark UI. So in the Spark UI, the last job ID was 6. Now let's go ahead and trigger the join. So it triggers two more jobs, which is 7 and 8. I'm actually wondering why it triggered two more jobs. Okay, it triggered three jobs. I triggered only one action over here, which is writing to a file, and one action should just trigger one job. So let's understand why it triggered three jobs. So you see there are three jobs over here, and it's it is it has 13 tasks, right? One task is going to operate on one partition, and if you recall, these 13 tasks resonate with something we've seen. So we have seen that the transaction data frame has 13 partitions, which could spin up 13 tasks, right? And the customer data frame has one partition, which could spin up one task, right, over here. And these are the two data frames involved in the join. So this essentially means something related to reading the file is happening in the first job, really reading the second file is happening in the second job, and probably the join is happening in the third job. So let's look at the stages, and in the stages you see that it read in this file, and then it also shuffled the data, because a join is happening and a shuffle would happen because of the join. And then it read in the second file and also shuffle that data, and finally the join happens over here in the third stage. So that is one of the reasons why Spark creates a separate job for reading and shuffling, right? So it created three separate jobs for this. Now let's have a look at how the SQL is going to look like. So if you read in the SQL, it basically scans your Parquet file for transactions, and then it also scans for customers. And in transactions, you see it has a lot of rows. It has around 39 million rows, and then it does the normal drill of columnar to row for both, and finally it does a filter. Now this filter is something that is added by Spark on its own as a part of its optimization and correctness process, right? So we don't see any filter being added by us. So this is added by Spark on its own, just to make sure that the join column is not null. And whatever output rows you get over here basically goes to the shuffle, right? So shuffling happens now. Similarly for this, the output rows goes to the shuffle, and you see that the number of shuffle partition is 200 for both of them. Is 200 for both of them, right? And this is a default number that Spark sets on its own. Now, from the exchange, there is another step happening which is called AQE shuffle read. Now, AQE is an optimization technique that has been introduced by Spark from Spark 3.0. And if you've seen an earlier video of mine, I've discussed AQE in a lot of detail. It basically stands for Adaptive Query Execution. And what it does is that it looks at runtime statistics, and those runtime statistics can simply be your size of partitions, the number of data partitions that have been read in, the size of your complete data, and all of that, right? And based on that, at runtime, it chooses the most optimal physical plan. Sorry, it's not optical, but optimal physical plan, right? So let's have a look at the optimization that it did, right? So here you see that it read in 200 partitions, but it finally coalesced it into 24 partitions. So it found out that all the other partitions are empty, and that is why it just reduced the number of partitions. And similarly for this one as well, it just reduced the number of partitions. But it actually read in 36 partitions, right, in the AQE shuffle read step, and then it reduced it to 24. Now, a very interesting thing to note is that in the step of reducing the number of partitions to 24, it also found out that there was a skewed partition. Skewed partition basically means that one of the partition has a lot more data than the other, and that is why it split up this partition into 12 partition, and finally reducing the 36 to 24 partition, right? So now once all of that is done, as a part of the sort merge join, the sorting happens over here, and then you get a final output. This project gives you the final column that you would expect after the join, and these two steps is adaptive Spark plan is final plan equals false. Now, as you've seen in my previous video, you would know that when we do an explain, it always writes something like adaptive Spark plan is final equals false, right? So as you also see over here, adaptive Spark plan, if we do an explain, it would always show it to be false, right? Let me do it over here. So if we do an explain, you would see the final plan to be false, because what AQE does is that at runtime it selects the best plan, right? But here we have not yet executed our query, right? We just want to know what the plan looks like. So that is why it shows is final plan equals false. But when you look on the UI, the execution has happened, and that is why you see its final plan true. And then finally, um, it just shows the right operation that we were trying to simulate using NOOP, right? So this is how your DAG is going to look like for a join. Now let's understand how it's going to look like for a broadcast join. And to enable the broadcast join, again, I set the threshold to 10 megabytes over here, and you just need to enclose the smaller data frame inside of f.broadcast, right? Now, a very important condition for broadcast join to happen is one of the data frame should be small, right? Small according to this property that you set over here. Yeah. So let's go ahead and do the broadcast join and see what happens. So now you see that it created two jobs. The first one is over here, and then the second one, right? So if we have a look at the stages, we see that the first one is the small data frame, and then the second one, probably where the join is happening, is the second stage over here. Here the broadcast is happening. The small table is being broadcasted to all the other the larger data frames, right? Now if we have a look at the SQL, we are going to see that this is the scan of the larger transaction data set, and the smaller data set is simply being broadcasted over to the larger data set. Yeah. So here there is a broadcast section which to show that, and finally the join is being done on the customer ID of both the tables, and you see an inner inside of the black box, and finally we select the relevant column, right? So this is how your DAG would look like for a broadcast join. Okay, so now let's look at aggregation operations. So in aggregation operation, we are simply going to do a group by city and then do a count, right? And then I'll simply do a show in order to trigger a job. Now let's see how that looks like. So here I am simply getting to see two jobs over here, and let me go to stages, and we basically see that the first stage basically reads in the data, which is 13 partitions, and then it shuffles because there is a group by involved, and hence it would do a shuffling, which is the first step over here, and then you finally get the output over here from the shuffle read, right? So let's have a look at how the DAG looks like. So again, we are doing a group by city and then doing a count, right? So what it would do is that it would first read the data set, and it would do a normal drill, that is columnar to row, and finally it does a hash aggregate. Now the important thing to note over here is it is doing a partial count, and the key that you see over here is the city. So it is grouping by city and then doing a partial count at a local level, right? So let's say in every executor you have, let's say, three partitions in total, right, sitting on different executors. So let's say this is partition 1, partition 2, and partition 3, right? So your data looks something like this. You have city a over here in partition 1, and then something like this, right? Now what it does is that it computes a count at a local level. So this is going to look like a2 b1, this is going to look like a1 b1 c1 a1, right? So that is what your first step is over here, the hash aggregate. Now what's going to happen is a shuffle. You see an exchange over here, right? So this shuffle is simply happening on the city. So if you have a look at this black box over here, it says exchange hash partitioning on the city, and the shuffle partition is 200, right? So it basically does a shuffling, and AQE does an optimization over here because the number of partitions were 200, and it finds out that most of the partitions are empty. You just need one partition, so it just coalesced everything into one partition. It reduced everything to one partition, right? So an exchange happened. Now after the exchange, how is the data going to look like? Because the exchange happened on the column city, which is this one over here, it simply means that all of the same keys for city are going to the same partition. So that means this comes over here, a2 comes over here, a1 comes over here, this a1 comes over here, this b goes to another partition, b1 they both come over here, and c1 basically stays at another partition, right? So the same keys go to the same partition. Now once that is done, we have the local count that were there in each of the partition. Now they have been coming together. Now we need to do a final count, right? Now the final count is the one that is being done over here. You see the hash aggregate, the key is the city, and then you do a final count. And after doing a final count, you simply say that A is 4, B is 2, and C is 1. And that is what you get over here as a part of the final step, right? So that is how your DAG is going to look like for a group by count operation. Now let's have a look at how it's going to look like for a group by sum, and it's going to look more or less the same. So this is going to trigger two more jobs for me. Again, the first one is reading, and the second one is computing the group by for me. So it reads the input, it does a shuffle because of the group by, and then it finally computes the values, right? So now we go to, let's try to understand how the DAG looks like. So again, you see it reads the file, it does a columnar to row, and then it does a local sum, right? It does a partial sum, right? Then the data is finally exchanged. AQE does some optimization, and you see is doing a final sum, right? So this is very similar to the count that we saw earlier, right? Okay, so now let's look at a slightly different operation. We'll look at a group by count distinct. This basically is the current state of the Spark UI, and let me go ahead and run a count distinct. So this is the DAG that is generated for a count distinct, and if we just have a look at it, we see that it's doing one exchange and then it's doing the second exchange, so it is doing two shuffles, right? An important point to note is that it is doing several hash aggregates. The first one is over here, the second one is over here, third one, and finally the fourth one. So it is doing four hash aggregates, right? And then we also see AQE shuffle trying to do some optimization, right? So let's take an example to understand what exactly is happening, right? So the example that we are going to use is something like this. Again, let's first revisit the question back. The count distinct that we want to do is simply group by customer ID and then a count distinct on the city. So we want to find out in how many distinct cities has a customer done a transaction, right? That's the end goal. So the example that we want to take is something like this. Let's say you have three partitions: partition 1, partition 2, and partition 3, and you have the customer ID, and the second one is the city. So basically customer did a transaction in this city, and what it's going to look like is something like this: A1, A1, B1, A1, B2, A1, B2, and then B1, B1, B2. This is again the customer ID and the city, customer ID and the city, right? So this basically means a given customer did a transaction in a given city. Now let's walk through the plan one by one. So the first one is a hash aggregate, right? And as you see in the black box, what it shows you is that the key is customer ID and city, and the function, the aggregation function, is empty. It looks a little different from what we've tried to do, right? Because we've tried to do a group by customer ID and then a count distinct. We've not done a group by customer ID and city, right? As you see over here. So when you see this, when the function is empty, it basically means that Spark is trying to do a distinct, right? So what Spark is trying to do is looking something like this. So it simply says, I'm trying to do a local distinct. So it simply does A1, B1, A2, B2, B1, B2. Now the reason why Spark does this is because number one, when you do a distinct, all of these are duplicates, right? Whether A1 appears once or 100 times, it doesn't matter. Ultimately, it is going to contribute the number one, right? That it the customer did a transaction in one city, right? So that is why it does a distinct. The numbers two reason is that it is going to help you transfer less data over the network. Now the exchange is happening, which is a shuffle, and as you see, the exchange hash partitioning in the black box shows you customer ID and the city. That means the exchange, the shuffle is happening on the pair, that is customer ID and the city. That means whichever pair is the same is going to go to the same partition. So this A1 is going to go to one partition, and there's only one A1. So okay, there's another A1. I by mistake wrote A1 as A2. This is going to come over here, all the B1s, which is B1 and B1, this is going to go over here, and B2, which is this one, and this one is going to come over here, right? So this is the third step after the exchange, basically grouping all of the common items together. And then you see AQE does an improvisation, because initially the number of shuffle partitions were 200, and then it found out that most of them were empty, and then it coalesced it into one partition, right? Then what we see is again a distinct is being done, right? Because let's say if multiple partitions had a customer doing transaction in city 1, and the other partition also had a customer doing transaction in a city 1, and both of them, when they come together, a distinct needs to be done again, because it doesn't make sense if you have two rows, because ultimately they are going to contribute one to count distinct, right? So this is going to have, this is going to be a distinct again, A1, B1 and B2, right? That is what you see as a step over here as a part of this hash aggregate. Now finally it does a partial count, right? The partial count at a local level. So from here you basically say that A represents that it went to one city, that this guy went to one city. This partition, what it tells you, went to one city. This partition again tells you that B went to one city, right? Now a final exchange is going to happen. This exchange is going to happen on the customer ID. Remember that we group by customer ID because we want to find the count by the customer ID. So final group by is going to happen by the customer ID, and finally you see a count is being done after the shuffle. So let's first emulate this step, the exchange, right? When the exchange happens, the same keys go to the same partition. So what you're going to see is this: A1 is going to stay over here, B1 is going to come over here, this B is also going to come over here, right? Now this basically shows that this exchange step is done. Now once that is done, we simply come to the final hash aggregate step, right? This hash aggregate step over here. So the hash aggregate step does a final count, right? Which is very simple. This is going to give you A of 1 and B2. That is what is the final answer, because A has visited how many? A has just visited, sorry, not visited, but actually done a transaction in city 1. B has done a transaction in city 1 and city 2. So that is what your final answer is, right? So here you see that there are two exchanges, right? Two exchanges are going to lead you to three stages, right? Because shuffles are the boundaries, and stages are basically the boundaries of shuffles, right? So if there is one shuffle, there are going to be two stages. If there are two shuffles, there are going to be three stages. So that is why you see three stages over here. And we saw two shuffles were happening, so you see two shuffle rights over here as well. So that is what you get out of the DAG, that you get out of a group by count. And I believe this gives you a comprehensive overview of how to read Spark DAGs for various operations, and then you can of course build on top of these operations, because most of the operations that we do on Spark is a mix of all of these, right? So I hope all of this that makes sense. It's great to see that you've completed the full video. If you found value, please don't forget to like, share, and subscribe to my YouTube channel. Thank you again for watching.